In this video, I want to focus on methods for actually solving linear systems of differential equations. And in this case, I want to focus specifically on homogeneous systems, meaning they'll all take the following form. So we're going to only focus on the following. So we're focusing on solving equations that take the form of x prime equals ax. So no plus f term. That term is not there. And that is what makes it homogeneous. So before we do this, to motivate what these solutions are going to look like, I want to think back to what it looked like if we were just trying to solve a single first order differential equation of this form. So instead of a vector x that contains a bunch of possible values of variables we're solving for, what if it's just one? So recall that the solution to a first order ODE of the same form, so not a system, looks like this. So basically what I'm saying is let's just take x prime equals some a times x. And because we're not dealing with vectors, we don't need a matrix here. We just have some constant here. And essentially what we're asking is, what is a function, x, where that function itself and the derivative of that function are equal to each other mod some constant? So we could rewrite this if we wanted and rewrite it in this form, x prime minus ax equals 0. And we could do integrating factor. We could have, excuse me, we could have separated by dividing by x and multiplying by dt and treat it as a separable equation. Either way, when we do this, we get exponentials for our solutions. And the solution winds up looking like basically some constant times e to the a t. So I'll call it constant 1. So basically, as we've seen in a couple of other cases, exponentials are probably a good place to start as guesses for what solutions might look like to this system of differential equations. So let's start with exponentials. So this suggests exponentials are a good place to at least start. Place to start. Okay, so let's take a look at the original equation that we were just talking about, the system of equations now. So consider x vector prime equals ax, and let's try to see if something of this form will work. So our x vector should look like some exponential, but it needs to be in a vector form, so I'm going to use the constants to be the vector. So instead of c, I'm going to call them k. I think our book uses k, so I'm going to call it k1 and k2. So that would just be a constant vector, but we said exponentials seemed like a good place to start. And so I'm going to do e to the lambda t. And the reason I'm going to use this letter lambda, we've seen this before when we talked about eigenvalues and eigenvectors. It turns out this lambda is going to have a similar meaning here. So it's not a coincidence that I'm choosing to use lambda here. So if that is our x, then that implies that our x prime vector will be the derivative. The constants wouldn't change. How do you take the derivative of one of these vectors? It's basically taking the derivatives of the terms individually. So constants pass right through a derivative. And when we take the derivative of the e to the lambda t, we would get back e to the lambda t with an extra factor of lambda. So we get lambda e to the lambda t. And so this is basically what we've got. Plugging these in, or subbing them into the system, we get the following. We get something that looks like this. So on the left, we have x prime, so that's going to be this term over here. So I'm going to have k1, k2 times lambda e to the lambda t. And on the right, we have a times the original x. So some matrix, I'm just going to call it a, we'll just leave it as a capital letter, times that vector. And x we have listed right here is k1, k2 times e to the lambda t. Okay, so this is what it looks like so far. Let's try to rearrange things. Let's move everything over to one side of the equal sign. So I'm going to do that by subtracting this term over to that side. And what we'd wind up with is basically a times our k1, k2, e to the lambda t, minus, and again, this is the term we're subtracting from both sides, so minus, let's pull that lambda out in front. Maybe that might make it easier to see. Well, whatever, let's just leave it here. We'll do that in the next step. So lambda e to the lambda t. And that's got to be equal to 0, but it's not just the scalar 0, it's the 0 vector. When we're dealing with vectors, and if I were to, for example, take the vector 1, 2 and subtract off the vector 1, 2, I don't just get 0, I got 0 on the top and 0 on the bottom. And this is what we call the 0 vector. So just keep that in mind. So let me delete that real quick. But keep in mind, that's what this 0 vector means. It means a 0 on the top and a 0 on the bottom. So here's what we've got. The next thing I'm going to do is factor out the k term and the e to the lambda t. So let's factor out basically the x part. So factor out the k1, k2, e to the lambda t. That shows up in both terms. And when we do that, something kind of cool happens. So I'm going to basically get a minus lambda. I'm going to leave a little bit of room here right after this because we're going to actually have to modify this in just a second, times k1, k2, e to the lambda t, and that's equal to the 0 vector. So the reason I left this space right here is the way that I've got it set up is A is a matrix. So A takes the form of something like this, right? It has some, I'm just using little x's to indicate placeholders for some numbers that go in there. Lambda is just a scalar. It's just minus some single number. So how do I subtract a scalar from a matrix? And the answer is we can't. But I need the matrix equivalent of this. And so the way that we do this is using something called the identity matrix. So I'm going to use the capital letter I, where I is equal to the matrix 1, 0, 0, 1. For us, on a 2 by 2, that's what it looks like. 1's along the diagonal, 0's everywhere else. And you could extend this if you were dealing with a 3 by 3 matrix, it would be the same idea. You'd have 1's along the diagonal, 0's everywhere else. And what this does is basically this is the matrix equivalent, the identity matrix is the equivalent of the number 1 in matrix form. And the idea is basically if you multiply any existing matrix times I, it doesn't change it. So like if I took A and I multiplied it by I, what you would get back is just A. It gives itself back. So that's the cool property about this. You can fiddle around and play with that. I don't want to focus a ton on it now, so you'll just have to take my word until you either take a linear algebra class or play around with the identity matrix more. But basically, I have a matrix. I can't subtract a scalar from the matrix. I need to subtract a matrix from the matrix to get this to work. They have to be the same shape. And to make this term be the same shape as this one, but still have the effect of subtracting this constant, I multiply that constant times the identity matrix, times the matrix version of the number 1. And so that is sort of the little trick that we're using here. This term here, you'll notice, is exactly how we defined x originally. Basically, we just factored out x. So this is x. We could make this term be 0, right? So we've got an equation now. I've got this stuff times our vector x equals 0. One obvious solution to that is that x itself could be 0, but that's called the trivial solution. We don't want the trivial solution, we want the non-trivial solutions, we want the interesting solutions. And this is where the idea of eigenvalues and what we talked about before, eigenfunctions, comes up. That's what we were trying to do in those problems. We were trying to find the interesting non-zero, non-trivial solutions. And that's essentially what we're trying to do here. I don't want this term to be 0, but I want this times this to give me the 0 vector. And that means I need this to be 0. Make this equivalent to 0. And I'm going to put 0 in quotes here because, again, what does it mean to, what we really have here are matrices. So what I don't need is 0, the individual number. I need this whole matrix to effectively act like it's full of zeros, in a sense, if you want to think about that. So that's the only reason I'm putting this in 0. Again, alternatively, we could have made this part be 0. If this part was 0, we'd get the trivial solution, and that's not what we want. So we want the interesting solution, so instead of this part being 0, this is the part that we need to make 0. Okay, so we want a minus lambda I times x to be equal to 0, the 0 vector, and we want to basically find the lambda that will make this work. So find lambda that makes this work. So our goal is, right, A is given in the original problem, presumably. We've got some system of equations that we're trying to solve. X prime equals AX, so I don't have control over A. I is predefined to look like this. Lambda is the only thing we have control over. So can we find a lambda that will make it so that this is true without forcing X itself to be 0? That is our goal. So essentially what we're going to do is the following. Think about what A looks like. So if the matrix A is, as we saw before, and I'm going to write it down just for a 2x2 case, but again, this extends higher. A minus lambda I is what we're interested in. If A looks like this, A11, A12, A21, A22, then what does A minus lambda I look like? Well, A minus lambda I, remember here's I, it's 1's on the diagonal, 0's everywhere else. So if I multiply this by lambda, what I'd get are just lambdas on that diagonal and 0's everywhere else. And if I were to subtract that result from A, what it means is effectively I'm subtracting lambda from A, but only along the diagonals. Everywhere else, I'm just subtracting 0. So we don't even need to bother to write that. So A minus lambda I is basically taking A11, A12, A21, A22, and subtracting lambda times 1, 0, 0, 1. But when I multiply the lambda constant through times this, it just turns those 1's into lambdas, and so we're just subtracting along on the diagonals, and we wind up with this matrix. A11 minus lambda, A12, A21, and then A22 minus lambda. And that is the matrix that we're dealing with here. So when I talk about A minus lambda I, this is the matrix A minus lambda I right here. And again, it extends to higher dimensions. You could have a 3x3 matrix, 4x4 matrix, but we're only going to focus on 2x2 matrices. So this is all you need to worry about for the time being. It turns out, and this is basically a theorem from linear algebra, so I don't want to dive into it too deeply. If you take linear algebra, they'll cover this in that class. But the only way to ensure that we can get non-trivial solutions to this turns out to be if this matrix, which is the same as this matrix, is what we call a singular matrix. So basically what it's saying is the only way to get non-trivial solutions is if A minus lambda I is what we call singular. And what it means for it to be singular is basically the vectors that make up the matrix. If we want to think about them as like this first column being a vector and then the second column being a vector, meaning the columns that make it up, columns are not linearly independent. And so what that means is if we were to kind of treat this like the matrix that we used when we tried to figure out if the two vectors were linearly independent, we talked about that. That's the Wronskian. So if I tried to compute the equivalent of the Wronskian for this, all it means is I'm trying to compute the determinant of, sorry, I'm pointing to the wrong one, over here, this one, to make sure that this column here and this column here are not linearly independent. All I need to do is basically take the determinant of this matrix, which is kind of the equivalent of the Wronskian that we talked about before, if we were to build the matrix up of these two separate columns, and make sure that it's equal to 0. This only occurs when the determinant of A minus lambda I is 0. So this sentence right here, if you're not familiar with a lot of this stuff, if you're not very comfortable with linear algebra, and again, I'm assuming that's where most people are, it may not make a ton of sense. But essentially, we talked about the Wronskian a minute ago. Pretend that we're just trying to check to see if this vector and this vector are linearly independent. That would mean that we need to compute the Wronskian. So we basically just build a matrix where we smush those together into a matrix and then compute the determinant. So it means this times this minus this times this. If that's equal to 0, it means our two columns are not linearly independent. And not linearly independent is what we want in order to get non-trivial solutions. That's the only way to get non-trivial solutions. So essentially, all this boils down to is we only get non-trivial solutions when the determinant of A minus lambda I equals 0. So this is the form that we're going to write this in. DET stands for determinant of this matrix. And again, we've computed that determinant. And it looks like basically what I mentioned a minute ago on a 2x2. You know, the ones on the diagonal you multiply, the ones off the diagonal you multiply, and you do these two minus these two. And that's what we're going to do, and set it equal to 0 and solve for lambda that satisfies that. So again, I'm not going to go into the details. If you're interested in this, we would go into enormous detail in a linear algebra class on exactly why this all occurs. You build up to it, but it's literally like weeks and weeks of work to go into all the details of exactly how this all fits together. For now, just know this is going to be our test. We're going to take A minus lambda I, compute the determinant, set it equal to 0, and solve for the value of lambda that allows that to be true. Okay, so just a quick couple side notes in case we've forgotten what those things are. The determinant of a matrix A is sometimes denoted with just vertical lines on the side of that matrix. And for us, it's basically A11, A22 minus A12, A21. So basically, if our matrix looks like the one that we just talked about, I'm going to go A11, A12, A21, A22, meaning this times this minus this times this. That's our little formula. So do that for this matrix, set it equal to 0, and solve for lambda. There's one other thing that may or may not come up. I haven't decided if we'll cover the section where we're talking about this, but if we want the inverse of a matrix A, the idea is we can find the inverse of a matrix, and what it means for a matrix to be an inverse is basically So what it means is if I take a matrix A and I multiply it by its inverse, we get the equivalent of 1. But what's the matrix equivalent of 1? It's that identity matrix. And it turns out you can switch the order. A inverse A or A times A inverse should both give you I. And that's what I'm talking about when I talk about the inverse of a matrix A. So this is the notation we use again, the normal notation for an inverse with a little -1 sign. And it turns out for a 2 by 2 matrix, this is pretty easy. It's 1 over the determinant of A, and then we just rearrange the terms in the matrix. So we swap the ones on the diagonal. This one is normally A11. It becomes, we put A22 there instead, and A11 goes down here. So we swap the positions of these two. The other ones stay where they are, but we flip their signs. And I did not leave enough room to flip the sign of this first one, so there we go. We may or may not wind up using this, but just figured I'd point it out. There's an easy formula to find the inverse of a 2 by 2 matrix. It's much more difficult to find the inverse of larger matrices, but for 2 by 2, it's not that bad. So just 2 quick notes. This is the one that's going to be important. This may or may not come up, depending on if we have time to get to it. Okay, so let's go back to what we were trying to do to begin with. So again, we want to find lambda such that the determinant of A minus lambda I is equal to 0. Okay, what that means is that the following is going to happen. So we find the following to happen. So the determinant of A minus lambda I is going to be the determinant, which I'll use straight lines for, of A11 minus lambda, A12, A21, A22 minus lambda. So that's what the determinant looks like. Remember, it's this times this minus this times this. So we get A11 minus lambda times A22 minus lambda. And then from that we subtract A12 times A21. And we force that to be equal to 0. So if we were to actually FOIL this out and kind of move terms around a little bit, what we wind up getting is, so let's FOIL this out. So I'm basically going to multiply these two binomials together. I'll get, when these two terms hit each other, I'll get a lambda squared. I'm going to lead off with that. So we'll get a lambda squared. The negative signs will cancel, and it'll be positive lambda squared. I'll get this one times this one, so I'll get a minus A11 lambda. I'll get a minus A22 lambda when those two hit each other. So the next term will be, we could write it as minus A11 plus A22 times lambda. And then the last term we'll get is the two constants times each other. So that's going to be plus A11 A22. And we still have this other term over here that I haven't touched yet. So minus A12 A21. And so this winds up being basically a quadratic in lambda that we need to solve because it's all now set equal to 0. Right, we set it equal to 0 and solve for lambda. I will again just use a little bit of stuff I should mention here. This term right here, we'll recognize that as the determinant of the original matrix A. If I hadn't done the minus lambda I, A11, A22 minus A12, A21, that was literally the definition right here of the determinant of the matrix A. And this term where you just add up the terms on the diagonal, because that's what this term here is, notice? It's just that term plus that term, or better yet, here we go, here's that term plus that term. That is often referred to as what's called the trace of the matrix A, and that's sometimes denoted TR parentheses of A. And it's just the sum of the terms on the diagonal. So this can be a short way to get there. It doesn't really matter, but again, just to tie in, if you've taken any linear algebra, you may be familiar with these terms, and you can kind of see that. So at this point, we call this thing that we got here, this big polynomial, this quadratic in this case, we call it our characteristic polynomial. And the lambdas that we find are the eigenvalues, and they can be used to construct our solutions. So this result, I should say, so this resulting quadratic in this case, but it isn't always a quadratic if we have higher order equation. But this resulting term is our characteristic polynomial. The lambdas that we find are our eigenvalues, and we're going to use them to construct our solution. And we'll come back to that solution in a minute. But before we do that, let's do an actual example, because otherwise it's all fine and dandy to do this in the abstract, but it makes a lot more sense once you actually use some numbers. So let's imagine that the differential equation we're trying to solve, or the system, looks like this. X prime equals, and our A is going to be, let's do 2, 3, 4, 3 times X. Okay, so we know to find lambda, all we need to do, first step, is jump straight to the determinant of A minus lambda I equals 0. That is our first step. So what is that determinant? Well, our determinant is going to be 2 minus lambda, 3, 4, 3 minus lambda. So again, it's the original A, but we subtracted lambda along the diagonals, and I'm now using straight lines here, right? These curly bracket ones or these rounded off ones, these indicate a matrix. When they're straight, they indicate the determinant of a matrix, which is going to be a scalar result. It's not a matrix anymore, and specifies that operation that we're talking about, where we take this one times this one minus this times this. So these straight lines indicate that we need to do that operation. It's 2 minus lambda times 3 minus lambda, and from that we're going to subtract off 3 times 4. And then that whole thing is going to get set equal to 0. So let's do a little work here. What is our polynomial going to look like? So same thing. I'm going to get a positive lambda squared out of it. I'm going to get a minus 2 lambda and a minus 3 lambda for a total of minus 5 lambda. And then I'm also going to get a plus 6 out of this. A plus 6, and then we have a minus 12 over here from the 3 times 4. And so far, so good. That all looks fine. And from this, we simplify to get lambda squared minus 5 lambda. That's going to be minus 6 equals 0. And now we just need to find those values of lambda. So what are the values of lambda? Well, we can factor this into lambda, let's see, lambda minus 6 times lambda plus 1. Should work, right? I need two numbers that multiply to give me the negative 6, but add to give me negative 5. So negative 6 and a positive 1 satisfy that. And when it's all said and done, we find out that lambda is either 6 or negative 1. Those are my two eigenvalues. So we get, after it's all said and done, that x needs to look like, coming back to the whole point of all of this, oh boy, we gotta go back a ways. Way back up here. Okay. We were trying to solve this equation. This was the form that we guessed that led to all of this. Now that I've found the lambdas, this is the form that my differential equation is going to take, right? We've got some basically vector times e to the lambda t. That was our guess for what our solution is going to look like. So that's going to motivate what I'm about to write. We get that x should be equal to some, I could call it like k1 and k2 times e to the first lambda value, so 6t, plus k3, k4 times e to the negative t. That is my guess. These can be thought of as constants that are vectors, right? We will specify these based on some initial conditions, but they play the role of our c's. If you want to think about it, you could think of this as our book uses k's instead of c's, but I'm going to call this vector k1, and I'm going to call this a vector k2. And so I know this notation is a little confusing. K1 and k2 here are just entries within a vector. So they're scalars. This is just some number, just some other number. But what that means is this whole thing is just some random constant vector. It's a vector with two numbers in it. Let's just call it, that whole thing, the k1 vector. It's some vector with two numbers in it. Same thing's going on over here. K3 is just some entry in a vector. K4 is just the other entry in that vector. They're both just constants. Let's call this whole thing just some constant vector. And so this is typically the notation that gets used to make things a little bit easier. So we would just write this as like k1 vector times e to the 6t plus k2 vector times e to the negative t. We do need to figure out the values of these two vectors, though. We can't just do anything yet. They need to also help satisfy the original equation. And it turns out they are what we call the eigenvectors. So in this case, these are the eigenvalues. And these are what we're going to call the eigenvectors. They're the vectors that correspond to, that allow us to get a solution that will work for what we're looking for. So how do we find these? So now we need the k vectors. How do we find them? Well, basically what we want to do is we've found the eigenvalues. Let's plug those eigenvalues back into the original setup of our equation that we had over here. So plug the eigenvalues back in. So for example, let's start with that first one. Which one did we say was our first one? Let's do the 6. So let's look at the lambda equals 6 case first. If lambda is equal to 6, my goal, remember, is to set it up so that, oh boy, hold on, here we go. We want this. This is the way that we've now rewritten our equation, right? We started with, okay, so let's go back to the theory here. We started with this differential equation. We said we want to find, assuming that our solution takes this form, which seems like a good guess to start with based on what we saw with single equations for first order differential equations. So we said, okay, let's assume this is the form of our solution. Plugging that form in led to this result right here. A minus lambda I times our x was supposed to be equal to the 0 vector. If we can find solutions that make this work, then we basically have found the x that will satisfy our original equation. So we basically transformed the original equation into this, into what we've got written right here. So I want to plug into a minus lambda I x equals 0. But now we know the values of lambda. They're either 6 or negative 1. So let's plug them in and find the values of x, so figure out exactly what those vectors have to look like in order for this whole solution to actually fit. Right, so when I say plug them back in, I mean plug them back in to a minus lambda I times x equals 0. So basically we're going to find the x's for which this actually works, right? This is the form of our equation. We know that x takes this general form, but we need the specific vectors sitting in front of these that are going to make that work. So let's just see how this pans out when we do lambda equals 6. So I'm plugging that into here. The original A, you'll recall, had a 2, a 3, a 4, and a 3. And all I need to do is subtract lambda along the diagonal. So in this case, minus 6 on those two terms. Times, here's the two entries that I'm calling K1 and K2, right? These are K1 and K2 scalars. They make up the vector, what that I'm calling K1 with the arrow over it, right? So this whole thing is what I'm calling K1, the whole thing. And we want that to be equal to the 0 vector. The 0 vector is 0, 0. Okay, so what that tells me is if we actually do this subtraction, 2 minus 6 will be negative 4. So I'm going to get negative 4, 3. Then I have 4, and then down here, 3 minus 6 is negative 3. And what you'll see is what we call a singular matrix. It's singular because either the two rows are multiples of one another, or the two columns are multiples of one another. Right? I can multiply this one by negative 3/4, and I would get this one. And that's what makes it singular, right? Basically the vectors that we smush together to make this matrix are proportional to one another. They are not linearly independent, and therefore our determinant was 0. So this should always happen. If you've found the correct eigenvalues, when you plug into this, you're necessarily going to get a singular matrix. And a singular matrix just means that this thing looks like this and this are proportional to one another. One is just a multiple of the other. That's always going to happen. And so, let me plug in my K1 and K2 here. And that's supposed to be equal to 0, 0. And so let's think about what this is telling us. If we go back to our matrix multiplication, and I were to actually write out the equivalent equation for this, what it says is basically, and I can do either one, because by design, they're going to give me the same result. It looks like a system for two equations for these two unknowns, but it's really just one equation because these two equations are proportional to one another. They aren't linearly independent. So if I looked at the top one, and I did my matrix multiplication, so this times this equals the top entry over there, I'd have negative 4 times K1, right? That's the first one here times the first one here, plus 3 times K2, so the second times the second. And that's supposed to be equal to the top entry over here. I could do the same thing with the bottom equation, but I would get something that gave me something that was basically an equivalent equation. All that it would differ by is some constant multiple that we could divide out. But our goal is to find a K1 and K2 that satisfy this equation. And it's nice, there's going to be an infinite number of them. By design, we'll be able to find basically anything proportional to what we're looking for here. One easy way to do it is to basically swap the two numbers that show up here, because I'm wanting these two things to add up to 0, this term and this term to add up to 0. So let's make this term be a 4 because we had a 4 up here, and this term be a 3 because we had a 3 right here, and make sure that at least one of these two, the sign differs. So in this case, the 3 matches the 3 exactly, but the 4 is the opposite of this 4. And so that will always ensure that we get the result we're looking for. So now I'll have negative 4 times 3, which will give me a negative 12, plus 3 times 4, which is a positive 12, and by design, those add up to 0. And we get out of this that vector, what we're calling K1, which is sitting right here, is K1, we said had to be 3, K2 had to be 4. So this is 3/4. And what I'm suggesting is, in general, you can find this very quickly by just taking the same two numbers that showed up right here. So this let's do it in color here. This one became this one became this one, and we just needed to flip one of the two signs. In this case, I could have flipped the 3 instead and had it be basically negative 3, negative 4, or 3 and 4, right? So I take the two numbers, swap their order, and plug them in, and then choose one of the two signs to flip. In this case, I chose to flip the negative sign to a positive. But again, any constant times this, so technically you have a constant sitting out here, any constant times this will work, right? I could have, instead of doing 3, I could have done 9 and 12 for these two numbers, and I would have had negative 36 plus 36, right? So we could plug in any constant times this, and it would also give us the eigenvector that we're looking for. Just pick a simple one. So in general, I will pick the easiest, simplest one. In this case, I'm picking 3 and 4. Oops, let me go back to that blue there. There we go. Okay, so that is one eigenvector. That will ensure that I get 0 when I plug in this particular eigenvector. Let's try, or sorry, this particular eigenvalue. This gives me the corresponding eigenvector. Let's try the other value. So when lambda is equal to -1, my matrix, remember it was 2, 3, 4, 3, but now I'm subtracting a -1 on the diagonals only. And I'll just call these, again, K1 and K2, even though we could have called them K3 and K4. It doesn't matter what you call them. This is a separate equation, but this is our second eigenvector that we're trying to find. So it's corresponding what I'm calling K2 over here, right? Basically, I just need to find these two vectors. We found K1, the one that corresponds to the 6, needs to be 3/4, or anything proportional to 3/4. 3/4, sorry. Over here, this is the one we're working on. I'm calling it K2, so that's why I'm labeling it K2 down here. This also needs to be equal to 0, 0, and we will see the exact same thing should happen. We should get a singular matrix out of this. So 2 minus a -1 is just 2 plus 1, that's 3. So we've got 3, 3, down here 4, and 3 minus a -1 is 4. And sure enough, notice that 3, 3, or 4, 4, they are proportional to each other. It doesn't make any difference which one we use to find our eigenvector. So what I'm going to do is immediately jump to K2 being equal to, I just take these two numbers over here. Sorry, let me write this a little more cleanly here. Take either of these two numbers. I could do 3, 3, I could do 4, 4, or I could do anything proportional to that. And I'm going to swap the order. So this 3 is going to go to the bottom, 3. This 3 is going to go to the top, 3. And I'm going to flip one of the two signs. So it doesn't matter, top or bottom. But it's a little bit cleaner if instead of using 3s, maybe it's a little nicer to simplify this, divide everything by 3. And so we could, because again, any constant times this will also work. But we can check, like imagine we plug this in right here. So that this was, so cross those out and imagine that we had our 3 and our -3 and do our multiplication. It'd be this times this, so 9, plus this times this, which is -9. So 9 plus -9 does indeed give me 0. But so would, instead of doing those two numbers, so would, come on now, there's the color I want. A cleaner version might be 1, -1, right? Just divide this whole thing by 3, both terms, and get an even simpler matrix, or a simpler vector here. And the same thing, if I plugged in a 1 here and a -1 here, I'd have 3 times 1 plus 3 times -1. I'd have a positive 3 plus a -3. They would indeed add up to give me 0. So in general, it's not wrong to leave it like this. It wouldn't be wrong to have it be 4, -4. It wouldn't be wrong to have it be -4, 4. But generally, I will try to write it in like the simplest way, if at all possible, to preserve integers for the values within these things. That is my preference, but you can do kind of, your mileage may vary, so do whatever you're comfortable with. But keep in mind, really, we do have any constant times this, any constant times this. So I'll call this C1 and C2. Just any constant times that will work. So the full solution is, when it's all said and done, the full solution is that x is equal to, here's our first eigenvector. So basically plug this in for our K1. Get it all on screen at once here. So I'm going to plug in 3/4 with that constant C1 out in front. So let's do C1 times 3/4 times e to the 6t plus some other constant C2 times 1 negative 1, and that corresponded to the e to the negative t term, right, where this was the eigenvalue. So e to the lambda t in both cases, and these are the corresponding eigenvectors. The C1 and C2, you can either think of them as being just tacked on here, or alternatively, you can think of this as being a solution. If we go back to the way that we use a fundamental set of solutions to form the most general solution, right? You can think of this as sort of our C1 x1 plus C2 x2 makes up the full solution x. So we do still have two unknown constants here. Those two constants would be determined by, so C1 and C2 determined by initial conditions. So that is the idea. So this is the approach that we're going to take to solve these things. It just turns out that there's one little wrinkle that comes up, and it's the same wrinkle that came up back when we were dealing with higher order differential equations. So this will be our approach in general. But there are three distinct cases. So the first case is we get real distinct eigenvalues, so real distinct values of lambda. That's the one that we just did, right? And you get your e to the lambda t terms. It's also possible, as we saw before, when if you want to think about it, where is it? The characteristic equation that we get here for lambda is almost identical to what we called the characteristic equation when we were dealing with second order differential equations, right? And they gave us two different values of what we were calling m before. Now we're calling it lambda. We just changed which letter we're using. But we basically had ones where we got real distinct values. If we get a repeated value, so real repeated case, and remember in the real repeated case, we wound up basically picking up, we'd have like an e to the lambda t term, and then the other one we'd pick up an extra factor of t, so it'd be t e to that same lambda t term. And that's what this is going to look like. And then the last case is if we get complex conjugate values. So complex conjugate lambda. And complex conjugate lambda wound up being the ones that, depending on if there was a real part or not, if there was a real part, we'd get still some exponential terms, and the imaginary part led to sines and cosines. And the same thing is going to be true here. We're going to get sines and cosines involved if we have complex conjugate values of lambda. So let's do examples of these. We've already done an example of this one, so let's just do examples of the other two. So let's take a look at this one. This is going to be an example of a real repeated value of lambda. And so if we want to go back and label this previous example, this one, I should note, is, now that we have dealt with lambdas, this is going to be the real distinct lambda case. So case 1. So here's case 2, real repeated lambda. What is one that works? So basically, again, we're trying to solve an equation that looks like this: x prime equals ax, where in this case, let's let our a be, in fact, let me just write it in directly. It is -6, 5, -5, 4 times our x. So this is the equation that I want to start. So the first thing we need to do is find the eigenvalues. And so this is typically how I'll do it to find the eigenvalues. All we need is the determinant of a minus lambda I equal to 0. So that's our starting point. So we can kind of jump to that characteristic equation without necessarily having to do too much here, right? So imagine that it's this minus a lambda and this term minus a lambda. Let's see if we can do it in our head. We could either write it out, or if not, if you can do it in your head, that's totally fine. So it's going to be negative 6 minus lambda times 4 minus lambda. And from that, I'm going to subtract 5 times negative 5, and that's supposed to be equal to 0. So if you can't get this equation in your head, what it came from was that our a minus lambda I, and the determinant of it, rather, I should say that, determinant of a minus lambda I is the following. So we need negative 6 minus a lambda, 5, negative 5, 4 minus lambda. So it came from doing this times this minus this times this. Notice a minus lambda I is just the original a with a minus lambda term applied to the two diagonal pieces here. And so this times this minus this times this, that's where I got this equation. If you can jump straight from this to the equation and bypass this line right here, trying to write it out like this, totally fine with you doing so. So just keep that in mind. So here's what that looks like. If we FOIL this out and clean it up, we'll get a lambda squared. So I get lambda squared. I'm going to get a plus 6 lambda and a minus 4 lambda. So plus 6 minus 4 is a plus 2 lambda. I'm going to get a negative 24, so minus 24, but I'm also going to get a plus 25, so minus 24 plus 25. And we wind up with lambda squared plus 2 lambda plus 1 equals 0. This thing factors to lambda plus 1, quantity squared equals 0. And what we get is that lambda is equal to negative 1, but it's repeated. It's a repeated root. Okay, so that means that we basically only have one solution, and we can try to find the eigenvector that corresponds to that one solution. So the next step is to find the eigenvector. If possible, if you have two different values of lambda, you find both eigenvectors. But now with just one, we'll just see what we get. So for the eigenvector, all we do is we're going to set our lambda equal to negative 1, and then solve a minus lambda I times x equals 0. And if you want to think about, we're calling it x here, you could, in a sense, call this the k as well. We want to solve specifically for the value of x that will make this work, but we're really just going for the eigenvector here. So we want the value of k that will make this work. Okay, so with that in mind, a minus lambda I is this matrix, but where we've subtracted negative 1 from the two terms on the diagonal. So what is that going to look like? So a minus lambda I, we're going to have, try to get this all on the screen at once, negative 6 minus a negative 1, 5, negative 5, 4 minus a negative 1, times, let's call them k1 and k2, equals our 0 vector, which is 0, 0, to make it totally clear. That cleans up a little bit. So the negative 6 minus a negative 1 is just negative 5. So we have negative 5, 5. On the bottom we have negative 5 and 5 again. And sure enough, we can see very clearly the two rows of this are not linearly independent. They're just multiples of one another. So choose whichever one is convenient for us to use. And I'm going to get that the eigenvector corresponding to this, I'll call it k1, is going to be, again, just these two numbers swapped in position, right? So here they would be swapped in position, right? This one went to the bottom, this one went to the top, and now flip one of their signs. So I'm going to flip that to a positive. But alternatively, we can pick something a little bit cleaner, and I'm just going to pick, instead of 5, 5, I'm going to pick 1, 1. Right? It's proportional to this one, It's just this one's scaled by a constant, but this is a slightly cleaner set of numbers to work with than 5, 5. So one solution is that I'll call x1, one of our two solutions, is going to be 1, 1, that eigenvector, times e to the negative t. Where the e to the negative t came from, it's e to the lambda t, and our lambda value was negative 1. So here's the eigenvector, and here's e to the eigenvalue times time. Here's the eigenvalue, negative 1. So this is one of our solutions. How do we get the second solution? Because we know we're expecting two solutions. So how do we find x2? There was only one eigenvalue, and in this case, only one eigenvector that we could get out of that. So how do we find a second solution? How do we find a second solution? Well, you'll recall the way that we did it before, using reduction of order in the original case and all that good stuff, led to an extra factor of t. And that's essentially what's going to happen here. It turns out that x2 will take the form of the following. So our second solution is going to look like this. It's going to look like the original eigenvector, so k1, times t e to the lambda t, plus some other vector, and I'll just call this other vector p. I think that's what our book uses, times e to the lambda t without an extra factor of t. We call this a generalized eigenvector. So this is the generalized eigenvector, this extra term that we have to add on. The reason for this particular form, I'll just demonstrate that this form will work and how we can figure out what this vector p should be, because we already know k1, right? That's this 1, 1 that we just found. We already know lambda, so we can have this piece, and this piece. This p is the only piece that we're missing. How do we find it? What motivates this particular form, again, requires a lot of linear algebra that we don't have time to go through right now. But it should make sense that we should see at least one term where an extra factor of t is picked up. And it turns out that if we'd tried just putting an extra factor of t in, it wouldn't quite work exactly. And so instead, if we generalize it a little bit more, we can actually plug it in and find what value of p will make this work. So the idea is, imagine we plug this in to the original differential equation, right? So again, we're trying to solve this differential equation. We can rewrite it in this form, and this is basically what we're trying to solve. After you rearrange, move this term over to the other side, and subtract off, our guess for the form of our x value, we would wind up with something that works out like this. So if this is what x is, what would x prime be? So x2 prime. And we'll just plug this back into the original differential equation. So we'll still have our k1, that's just a constant, but now I have the derivative of this, and we've got to do product rule here. So it's going to be that term times first times the derivative of the second. So I would get an extra factor of lambda, so it'd be lambda t e to the lambda t. That's the first, the t, times the derivative of the second, which is lambda e to the lambda t, plus second times the derivative of the first. So plus second times the derivative of the first would just be that. So here's the derivative of this, plus what we're calling this vector p times another lambda e to the lambda t. So there's what x prime looks like. And all we need to do is basically verify that this works. So plug into the original ODE. So on the left, we have our x prime term. So that's our k1 times lambda t e to the lambda t plus e to the lambda t plus our p lambda e to the lambda t. So that's the whole left-hand side, right? That is just x2 prime. And that's equal to a times x. So again, I'm just plugging into right here. I'm plugging it into this equation, but just doing so kind of generically now. So we've plugged in the left-hand side. That was all of this. That was our x2 prime term. Times a, there's our a, times the original x. And here's the original x. So the original x looks like, come on, there we go. Looks like k1 te to the lambda t plus p e to the lambda t. Okay, and so I'm basically going to just group some terms together, move some stuff around. Let's get all the terms that involve the te to the lambda t moved over here. So I will get basically this term and this term. Let's move everything over to the left-hand side. So we're just doing some algebra. I'm just rearranging terms. So over here I have the following. I'm going to have a minus lambda I times k1 te to the lambda t. So far that is, we have our a k te to the lambda t. Here's our a k te to the lambda t. So there's this term here corresponds to this one here. And so really, I guess I'm moving this one over to the other side there. And then I'm subtracting off lambda, and this I, again, plays the role of 1. So just lambda k te to the lambda t. And here's our lambda k te to the lambda t. So that's this term moved over to the other side so that it now has a minus sign. So basically, this term right here became this term right here, kind of. Let's write the whole thing out. And then this term over here became this part of that term right there. So we've taken care of those two pieces. We also have on this side plus a minus lambda I times these p terms. So p e to the lambda t. And that is, again, let's pick another color. So the a times pe to the lambda t, that's this part. And then let's do yellow over here. Here was just p times lambda e to the lambda t, and here's that term right there, the p lambda e to the lambda t, and it got moved to this side, so it now has a negative sign associated with it. So there's that, plus this one last piece that we haven't accounted for, k1 e to the lambda t. And all of that is supposed to be equal to 0, because we've now moved everything over to one side of the equal sign. So pick a last color here. This term here was this term here. And can't forget the k that was multiplying it. So there's all the pieces. We just moved all of these over to this side. Oh, and I missed a sign. That should be a negative sign now because I did move it over to the other side. Let's not screw that up. So that's a minus sign there because this got moved to this side. Okay. So with all of this, basically, I want this thing to go to 0, right? For this whole thing to go to 0, I need these terms to go to 0. These are the ones that are proportional to, so these are the te to the lambda t terms. And these ones over here are the e to the lambda t terms. There's nothing in this one that can cancel anything over here. There's nothing here that can cancel anything over here. They're separate. So for this sum to be equal to 0, no cancellation between these terms are going to occur, so they each individually have to be 0. This must be 0, and this also separately must be 0. And so this is what gives us our two equations of interest. One of them is that basically a minus lambda I times our eigenvector k has to be equal to 0, but we already knew that. That was kind of by design. That's when we solved for this term right here. When we solved for this k, that was by design. That's exactly what we were doing there. But the second equation over here, again, if you factor the e to the lambda t out, what it's saying is that a minus lambda I times that p vector, this new vector p that we don't know anything about yet, so that's this part, minus k has to be equal to 0. So another way of saying that is that has to be equal to k. This is what would force this to go to 0, so that this term would cancel this term. So if a minus lambda I times p was the same thing as k, then this term subtracting this term, they'd be equal to each other and we'd be subtracting them, and they would go to 0, exactly as we want. So this is the condition that we need to find p. We need to ensure that this happens so that this whole term goes to 0. So this is already satisfied automatically. We've already done this, and this is how we find p. So basically, you don't need to go through this every single time. All you need to do is memorize this is the form our second solution is going to take, and the way to find p is basically jump to the same matrix times our unknown vector p has to be equal to the eigenvector that we already found, right? So this p is our generalized eigenvector, and we need, in this case, a minus lambda I. We already did a minus lambda I. That's how we found k to begin with. This is a minus lambda I. So it's negative 5, 5, negative 5, 5. There's our a minus lambda I. Here's our unknown vector, p1, p2 being the two entries of it, and it's got to be equal to k. K was 1, 1, or what I'm calling k1, I guess, is 1, 1. And so now we need to solve for something that will satisfy this. For most people, it's easier to not try to do this in matrix form. What we really have is negative 5 times p1 plus 5 p2 equals 1. Right? So this times this plus this times this equals the top entry. And again, you could have done the bottom one instead, and you would have had an either identical or at least identical mod some constant equation. And so again, we don't have to find we don't have to find a specific value. We have one equation here with two unknowns. There's going to be an infinite number of solutions here. So pick any P1 and P2 that works. So for us, make life easy, pick one of them to be like 1, or better yet, pick one of them to be 0. So I'm going to let P1 be equal to 0, just because that's easy. If P1 is 0, then we'd get negative 5 times 0 plus 5 times P2 is equal to 1. And so what would make this true? So this whole term is now 0. What do I need to make P2 in order to force this term to be equal to 1? P2 is equal to 1/5. And so that would give me one option. So the vector P would be, P1 would be 0, and P2 would be 1/5. So there's one option. But we didn't have to do that. We could have let P2 be equal to 0, and that would have given us, alternatively, negative 5 times P1 plus 5 times 0 equals 1. So same equation here, but now I'm saying let's force this one to be 0. And that means that P1 has to be equal to negative 1/5. And so we could have found a different P that would have worked equally well. Negative 1/5 for P1, 0 for P2. Or you could have done some other combination, but they're only worse. So the easiest way is just pick one of them to be 0. Either of these are fine. So when we finally construct the whole solution, we get that x2, our second solution here, remember, is the original eigenvector. So it's going to be 1, 1 times te to the lambda t, so te to the negative t, plus p, which we just found is either of those. Let's do 0 and 1/5 times e to the negative t. So there's what x2 should be, right? There's p, there's our k1, and it just takes this general form that we prescribed up here. That's basically just what you need to memorize. And again, our generalized eigenvector right there is that value p that we found. Okay, now that we found x2, we can construct the general solution. So we now have two, by definition, linearly independent solutions, and our general solution is that x is equal to c1 x1 plus c2 x2, which for us is c1 times x1. x1 was 1, 1 e to the negative lambda t, plus c2 times x2 is this thing that we just found. So 1, 1 t e to the negative t plus 0, 1/5 e to the negative t. So there is our general solution. This is our x1. This big thing was the x2 that we just found. So definitely a lot more work, a lot more of a pain in the butt to do these repeated eigenvalue problems. And again, I know it's going to feel weird. Why do we guess this form? And for now, again, without going into a ton of linear algebra, I'm afraid the best I can do is because. But we verified that we can, in fact, find a solution that works. We just plugged in and found something that satisfies it. So we know that at least it is a form of a solution that will satisfy the original equation. And therefore, it must be a solution. We know it's linearly independent because it has this extra factor of t, and for a number of other reasons. It's definitely linearly independent from this one over here. Okay. Final case, last case. So final example. We want case 3, where we have complex values of lambda. And so let's pick a problem. X prime equals, let's see, 4, 5, -2, 6. I'm not just coming up with these on my head. I came up with it ahead of time, found one that would work. So this will work. First step is to find the eigenvalues. And we do that by setting the determinant of a minus lambda I equal to 0. And then the second step after we find those eigenvalues will be to find the corresponding eigenvectors. So if we plug in our specific matrix here, what we wind up with is, let's see, it'll be 4 minus lambda times 6 minus lambda minus, we have 5 times -2 equals 0. And so from that, we're going to get lambda squared. I will get a minus 6 lambda and a minus 4 lambda for a total of minus 10 lambda. And then over here, we're going to get a, what is that, plus, oops, let me not forget this term, plus 24. So I'll get a plus 24 from there. And then lastly, a plus an additional 10 from these two guys here. And that's equal to 0. So we know that in this case, it's not looking good for being able to factor this. We can either complete the square or use the quadratic formula. If I were to complete the square on this, we'd get lambda minus 5 squared. That would give me a plus 25, but I don't have a plus 25. I have a plus 34, so that's plus an extra 9. So an extra 3 squared. So there it is rewritten. If we solve for lambda, we will get that lambda is equal to, so we'd move this over to the other side, take the square root of both sides. It'll be negative, so we'll get plus or minus 3i. And then at the end, we'd have to add a 5 back. So we're going to get 5 plus or minus 3i. So there are my complex eigenvalues. They always come in complex conjugate pairs when they're complex, right? By definition, that's how the quadratic formula works, for example. So there's not really any additional difference or extra information given if we compare the 5 plus 3i compared to the 5 minus 3i. So even though it looks like we got these two distinct eigenvalues, they're always going to come in these pairs, and there's not really extra information encoded in like the second solution. If you know that you got 5 plus 3i as one eigenvalue, the second one automatically is 5 minus 3i. So we don't actually have enough information to get basically both eigenvectors from this. So they always come in pairs. And so basically we don't even need to use both. So there's not any extra info in the lambda equals 5 plus 3i versus the lambda equals 5 minus 3i. We're really going to only wind up needing one of them. So to find the eigenvector, and we'll see this in a minute, but to find the eigenvector, or vectors in this case, we're going to go back to our same old. So we're going to do a minus lambda I times the vector of interest. We can call it x, we can call it k. I think I've been calling it x. Maybe this time just make it easy and call it k. Jump straight to it. That's what we need to find. So if I did, for example, lambda 1, the first one, and did 5 plus 3i, what we'd get from that is that our matrix A minus lambda I would be, so 4 minus 5 plus 3i, then we have a 5, a negative 2, and then a 6 minus 5 plus 3i times the two components of our eigenvector is supposed to be equal to 0, 0. Okay, if we clean this up a little bit, I'll get 4 minus 5 is going to be negative 1. The negative sign also distributes through to the 3i, so it'll be negative 1 minus 3i, 5, negative 2, and then down here it's 6 minus 5 is positive 1. And again, that minus sign distributes through 1 minus 3i. So there's what that one looks like. Times k1, k2 equals 0, 0. And it looks like these two rows are not linearly independent. They look very different from one another, but it turns out they are always going to be linearly dependent. So it isn't going to matter which one we pick from this. You can basically check that out. You could find, for example, what am I going to have to multiply one of these by in order to get the other one out of here? So for example, oh boy, to make these proportional, I would need to multiply this bottom one by, it's negative 2 times some stuff, and I want that to be negative 1 minus 3i. So I'd have to have a 1/2 plus 3/2 I. And it turns out if I were to multiply this term by that, right, distributing through, that would be a negative 1 and a minus 3i. I'd get the top. And if I took this exact same thing and multiplied it by this, it turns out we would get 5 out of that. We could check just real quickly to show that they are in fact proportional. So let's just see what we'll get out of this. I'd get 1/2 times 1, so I have a 1/2. I'm going to get 1/2 times negative 3i, so I'll get minus 3/2 I plus 3/2 I. Those cancel. And then lastly, this times this. So I'm going to get negative 9/2, but times I squared, which is negative 1. And so we have 1/2 really plus 9/2, which is 10/2, which is 5. So by finding the appropriate factor, we can multiply one of these by that constant and you get the other one. So they are indeed proportional. And going forward, we shouldn't have to check that every single time. Just pick one and assume that if you've made everything else correct, they will always be proportional to one another. So this is going to give us a vector for our first eigenvector that I can get by just taking these, again, two entries, swap the order. So it's going to be 5 on top, and the 1 minus 3i, or negative 1 minus 3i on the bottom, but I just need to flip the signs. So it's going to be 1 plus 3i on the bottom. So there's my first eigenvector. So from here, if we were to try the second eigenvalue, which was 5 minus 3i, it turns out that what we'll basically get is a result that isn't really fundamentally different from the one that we just got. So I'd have 4 minus, now it would be 5 minus 3i, 5, negative 2, 6 minus 5 minus 3i, times the unknown k values. That's supposed to be equal to our zeros. And we'd simplify that and get, let's see, so 4 minus 5 is going to be negative 1 plus 3i, 5, negative 2, 6 minus 5 will be 1, and that minus sign distributes through, and we get 1 plus 3i times k1 and k2. And from that we would get, in this case, so that's got to be equal to zeros, sorry, but that would give us a k2 that looks like, take that first one, swap the order, flip the sign, so it'd be 5, 1 minus 3i. It basically looks the same as this one, where k itself is the complex conjugate of the other k. Right? So not only are the eigenvalues complex conjugates of each other, meaning they have the same real part, but the imaginary part, the sign is flipped. Same thing is true of the two eigenvectors. Real parts are the same, 5, 5, positive 1, but the imaginary parts have the signs flipped. So basically, we didn't really need to do this extra work here. This will always happen. Once you have one eigenvalue and its corresponding eigenvector, know that the other eigenvalue, its eigenvector will be the complex conjugate of the original eigenvector. So we don't need to do this extra work. So notice that that will always happen. We can kind of skip that second step. Always complex conjugate of k1. k2 will always be the complex conjugate of k1. And our solution is basically that x is equal to c1 times k1, so that was 5, 1 plus 3i, yeah, 5 times 1 plus 3i times e to the 5 plus 3i times t plus c2 times 5, 1 minus 3i e to the 5 minus 3i times t. And so there is our solution. But obviously this form of the solution sucks. I don't want i's in my solution. There were no i's in the original framing of the problem. Why should I have i's in my solution? So let's convert these exponentials with complex parts, with imaginary parts, into sines and cosines. So recalling Euler's formula, we know that basically e to the, let's do that first one, 5 plus 3it is really e to the 5t times cosine of 3t plus I sine of 3t. And the other one, e to the 5 minus 3i times t, it will be e to the 5t. And for its part, we will also get cosine of, we basically would get cosine of negative 3t, but because cosine is an even function, cosine of negative 3t is the same as cosine of positive 3t. And then sine is an odd function, so we'd have plus I sine of negative 3t, but sine of negative 3t is negative the sine of positive 3t. So this sign just flips because it's an odd function. That way I don't have to have negatives inside the arguments of the sine and cosine functions. So we get a plus here because cosine's even. We get a negative sign here because sine is odd compared to the line above it. Okay, so with this in mind, we really get, comparing these, we get that x is really equal to c1 times 5, 1 plus 3i on the bottom. There's the vector. And this term we can now write out long ways like this. E to the 5t cosine of 3t plus I sine of 3t. And then the c2, we get 5, 1 minus 3i e to the 5t cosine 3t minus I sine of 3t. So just plugging in these two parts that we just found. If we do a little bit of algebra, we can clean this up. So what I want to think about is basically writing this as an actual vector, so kind of top and bottom parts separately. So basically what I'm going to imagine is on top here, and I want to group like basically real and imaginary parts together. So we've got on our top, we're going to have C1, 5e to the 5t times cosine 3t plus I sine of 3t. So that's our top of this. So this times the whole thing, plus c2 times 5e to the 5t cosine 3t minus I sine of 3t. So there's the top. And the bottom will be this whole mess. So on the bottom we get c1 times, let me actually do this multiplication here. So c1 times, we will get the 1, let me do just the real part, 1 times e to the 5t times this whole thing. So e to the 5t times cosine 3t plus I sine of 3t. Now let's do the 3i part. So c1 times 3i e to the 5t. So the next one is plus 3i e to the 5t cosine 3t plus I sine of 3t. Close my parentheses. So basically I've split up the 1 times this whole thing and the 3i times this whole thing separately into these two pieces. I need to erase this because I did not leave nearly enough room, because now I haven't even touched C2 yet. So plus C2, and again on the bottom we'll get the 1 times this whole thing and then the negative 3i times this whole thing. So the 1 times this whole thing is going to be e to the 5t cosine of 3t minus I sine of 3t. And then we're going to get minus 3i e to the 5t cosine of 3t minus I sine of 3t. Close those parentheses, and there is my incredibly long, ugly vector. This is the top entry. This whole mess is the bottom entry. The point of doing this isn't to just make things worse. It's going to eventually make things better. And I promise you, you don't need to do this on every single one of these problems. It's just to come up with a form that we'll be able to sort of copy going forward. So I want to split up the real and imaginary parts kind of separately here. So let's see how this looks. The next thing I want to do on top is group the real parts together. So the real parts are going to be, in this case, this term is real, as is this term. And so they both have an e to the 5t. They both have, in this case, a c1 and a c2 in front of them. So I'm going to write this as c1 plus c2, 5e to the 5t cosine of 3t. So there's what we got by multiplying, basically pulling out this term, and grouping them together. Now let's do the imaginary ones. I'm going to have plus I, so I'm factoring out the I that shows up in these two. We're going to have C1 5e to the 5t, so we're going to have a C1, we'll come back to that in a minute, 5e to the 5t sine of 3t, so that's this term. And over here, we're going to have a minus C2 of them. So minus C2 times the same, 5e to the 5t, but now the minus sign is taken care of, I sine of 3t, so sine of 3t. So we just had a minus C2. So if you don't trust what I just did or didn't follow, just basically group the real terms together, group the imaginary terms together. These become the new coefficients. So there's what the top is. Real over here, imaginary with the I factored out over here. Now let's do the bottom, which is going to be obviously even worse. So the real terms, I'm going to get this piece. I'm going to get this piece, because this I times this I will become a -1, so that'll be part of it. I'm going to get this piece, which is real, and then this piece, which will wind up being real. That I times that I will also become real. So we're going to actually have like 4 pieces in the real part here. It's going to look like, let's get all these together. We're going to get C1 plus C2 e to the 5t. We've got cosine of 3t for that term, because that is, I've grouped this term and this term together and just factored out the C1 and the C2. C1 plus C2, they each were hit with one of those, so that's that term. For the ones that involved I, it's going to be this C1 times this term. So what are we going to get there? We're going to get minus a C1 plus C2. That's actually also going to wind up being C1 plus C2 times 3e to the 5t times the sine of 3t. So that is C1, 3. This I times I makes it negative. And we get the 3e to the 5t, 3e to the 5t times the sine of 3t. So the C1 part is this term. And then the C2 part is this term. C2, a -3, but this times this will become positive. So I actually got to, I messed that up. So I messed up the sign here. This needs to be a negative sign. There we go. That looks better. So there's that term. Those are the real parts. And the imaginary parts are going to be the remaining parts that survive. Let me just write them out because it's going to be a nightmare otherwise. Did I get that right? No, that should be a plus sign there. I think I just messed up. Right. That negative became positive, then I and I made it negative. So yes, it should be negative, which it is if I distribute that through. Okay, so that is plus. I was good the first time. Sorry about that. Okay. The next terms are the imaginary terms. So we're going to get plus, in this case, I. It's going to be C1 minus C2 e to the 5t times the sine of 3t. So that is going to be the combination of, again, the imaginary terms. So that's this term right here, C1 e to the 5t sine of 3t. So that's our C1 times those. And then the second one came from, where is it? This one, C2 e to the 5t sine of 3t, but with a minus sign, because that's a negative. So I've taken care of that term and that term. And now the last ones are this term and this term, which are imaginary due to the i's sitting right there and right there. So that last piece will be plus I times C1 minus C2 times 3e to the 5t cosine of 3t. So I've condensed it a little bit After all that, the idea is that these C's that show up only show up in two combinations, C1 plus C2 or C1 minus C2. And so I'm going to call those two things new constants. I'm going to let C3 be C1 plus C2, and I'm going to let C4 be C1 minus C2. And that will help a little bit. We will now have, after it's all said and done, and in fact, let's actually make this C4 be real. Let's put an I here, because it only appears as C1 minus C2 times an I. C1 minus C2 times an I. C1 minus C2 times an I. So let's put that I as part of it. And now we don't have any imaginary parts. We'll roll that into the constant. And we'll have C3 times 5e to the 5t cosine of 3t plus C4 5e to the 5t sine of 3t. Right, so that's these ones on top. And then on the bottom, I've got this whole mess. We're going to get C3. Where does C3 show up? That's this one. It shows up here and here. So it's going to be e to the 5t cosine of 3t minus 3 sine of 3t. Okay, good. Plus C4. So that's this one and this one. And we've got e to the 5t times what? Sine of, come on now, sine of 3t plus 3 cosine of 3t. So I've just kind of, again, factored out some terms, grouped stuff together. This algebra is getting bad. I know you're probably exhausted. Follow it carefully. I don't think we've made any mistakes yet. And lastly, we can clean this up a little bit. So let me factor the C3 out and the e to the 5t out and see what I can get out of this. So this first term, I've got a 5 on top, a 1 on the bottom, times cosine of 3t. And from that, I'm subtracting 0 and a 3 times the sine of 3t. You can write it like that. And I basically hit all these terms over here with a C3. So I basically split it up. The cosine terms here corresponded to a coefficient of 5 on top and 1 on the bottom, 5 and 1. And the sine terms, there was none on top, so 0 on top, but there were 3, or rather negative 3 on the bottom. So here's our negative 3 on the bottom. So there's that piece. Plus, now let's do the C4 terms. They also have an e to the 5t that's been pulled out. And we're going to get now for the, get a 5, 1 for the sine of 3t term. Right? 5 of the sine of 3t is on top, just 1 of the sine of 3t is on the bottom. And then for the cosines, we have 0 on top and 3 on the bottom. So plus 0, 3 cosine of 3t. Okay, so after it's all said and done, let's notice a couple of things. Notice the 5 and the 1. These are the real parts of the eigenvectors. And the 0, 3, these are the imaginary parts of the eigenvectors. Meaning, if I go back and compare to the original eigenvectors that we found way up here they are, right? The real parts were 5 and 1, and then the imaginary parts were 0 and 3. And that's exactly what we got here, 5 and 1, 0 and 3. And what this tells us is that in general, we have a form for our solution. So this is what the solution is going to look like. But in future problems, you're not going to need to go through all of the algebra from here down to here, you're going to be able to skip it and jump to just a general form. And that form is, so in general, the form of the solution if basically our lambda is equal to alpha plus I times beta is the following. So if our eigenvalue is lambda equals alpha plus I beta, in ours it was 5 plus 3i, I think, plus or minus. Where the heck is it? 5, yes. There it is, 5 plus or minus 3i. So 5 plus or minus, so in our case, alpha plus or minus I beta. We're going to get the two solutions to be the following. x1 is going to be the following. It's going to look like basically some constant. We can call it kind of whatever we want. I'll call it, I think we've used a capital B yet. So b1 cosine of beta t minus b2 sine of beta t times e to the alpha t. So that's going to be our x1. Our x2 is going to be equal to b2 cosine of beta t plus b1 sine of beta t e to the alpha t. So notice that basically the coefficients got switched around on the cosine terms. One was b1, one was b2, and then relative to the sine terms, it's the opposite. So that's kind of what happened here, right? Here 5,1 was with the cosine term, over here 5,1 was with the sine term. So that's what I'm suggesting here. Alternatively, 0,3 was with the sine term, and now 0,3 is with the cosine. But in this case, the signs have flipped. So notice the signs flip on the sine terms. All of this is where our b1 is just the real parts of our eigenvector, and b2 are the imaginary parts of that eigenvector. So where k1 is the eigenvector, the one eigenvector that we found. It doesn't matter. So we can jump straight to this form. So for us, our x1 in this case would be the real part of the eigenvector. That was the 5,1. So we're going to have 5,1 times cosine of 3t, 5,1 times the cosine of 3t, minus the imaginary parts. That was 0,3 times the sine of 3t, 0,3 times the sine of 3t with a minus sign, all times e to the alpha t, and alpha was our 5, so e to the 5t, e to the 5t. So there, this whole piece from here to here takes the form of our x1 times some constant. Over here for x2, it's going to be, again, b2, so that was our imaginary parts, that's our 0,3 times the cosine, 0,3 times the cosine, plus b1, b1 was the real part, so that was our 5,1, 5,1 times the sine of 3t, 5,1 times the sine of 3t, and then all of that times e to the 5t, e to the 5t. So in our case, the alpha was 5, right? And we can basically jump straight to this formula. Again, just basically worth memorizing so that you don't have to go through all of this algebra on every single one of these problems. Right? Doesn't matter if we call them C3 and C4 at the end of the day, we can just go back to calling them C1 and C2. We can, use different names. K1 and K2 have been reserved for other things, but pick whatever letters you want for your two coefficients. And our general solution looks exactly like what we've got here. Some constant times our x1 term plus some other constant times our x2 term. So keep that in mind. You'll get some practice doing this on the homework. So on the homework, give it a shot, see how it goes, but don't go through the algebra I went through, jump straight to the formulas. Get used to using these formulas, okay? Good luck.